So, hello everyone. So, my name is Tosi Palam. So, I will be holding sessions for this fluid dynamics for astrophysics course that has been taught by Professor Prasad Subramanian. So, before I start, I want to know some of you. So, okay, can you let me know that you are with me? So, we have 10 people in our meeting. Okay, so we have Bharti, Arti Bharara, अतुल भट्ट, अभिक दास, दृश्य एस, माइनक चंद्र, मनीष कुमार, मुस्कान परवीन, शरण कार्तिकेयन. It's good. So I assume you all are MSc students or completed your MSc.
Sir, I'm a BSc student.
Okay. BSc which year?
Currently in second year.
Oh, okay, okay. So I guess nowadays take you can take credit for this NPTEL courses also, no?
Yes, sir.
Yeah, that will be useful for your CPI.
Okay.
Okay.
Yes, sir.
So, and others, are you all BSc, or I just want to know, uh, my students, they're all BSc or MSc, on which level I need to describe things. That's why. So, I think there is also chat box. If you're not comfortable in talking, I think you can also. Yeah, and also the session is being recorded. Okay, I hope you don't have any problem with that. That is the rules for any session. So I will upload the sessions uh, in my YouTube channel, and the link will be shared with you all so that you can, if any one of you missed, and will have an opportunity to see that. And what are the other things? Okay, there is some chat box, no, you guys. Okay, there is some chat box also. There is some attendance thing. Okay.
Space.
Hmm. So yeah, so without any, I think, yeah. Have you any of you responded? Are you like all BSc or MSc or? Hello.
Yes, sir.
Yeah. Okay. So let's start our session. If you have any problem, just let me know. Uh, yeah. So continual limit. So we know that we deals about things or system of particles based on two scenarios, on macroscopic and other is microscopic, right? So for macroscopic, we know the temperature is important. I mean, we can just know the temperature of the whole body, right? These are the macroscopic features: temperature, conductivity, how heat is conducted through the material. That is all over the same for the whole material. We don't deal with the particles. But for microscopy, we deal with the particle collisions, right? So the particles' natures and their collision with each other plays a role. There are some other factors. Can you guess what are this question mark for macroscopic and microscopic? Yeah, so for macroscopic, the other question mark things, I think, yeah, I will show you. So another thing is pressure, right? So because pressure is also how pressure is defined. So it is the force acted on the surface. So if it is in equilibrium, so the pressure is uniform all over the body, right? So that is also a macroscopic quantity. For microscopic, thermal motion is also important. So, like for each particle, we know the temperature is nothing but the manifestation of each particle's kinetic energy, right? So, the thermal motion of each particle. So, that is also microscopic. And there's other transport phenomena. So, I think that will come later in that course. So, that is also a microscopic quantity. Am I audible now?
Yes, sir.
Okay. Thank you.
Yes, sir.
I started recording, then I don't know, I give the full screen, I quite confused what if it is recording or not. Because if it is not recording, then they will again make me record the whole thing. So stop recording. Okay. So then the continuum limit. Okay. So this continuum limit, it holds good when, can you guess? I mean, when when it can tell us about the things that it is okay. The study of each particles so will be important. Okay, let me take it to you. I mean, I don't ask too many questions right now. So it holds good when the number, right, the number of particles in that body, like talk about so like even if a ball, so if it like made of pure iron, okay, so it made of pure iron. So iron is 56, right? It's molecular number 56. So if I take a ball of 56 grams, so it will contain Avogadro number particles, right? That is very much like 10 to the 23 order. So then it will hold good this microscopic or macroscopic nature. But suppose the system based on only one particle, like just or one or two particles. So then there is no meaning of macroscopic nature, right? Because they can act individually, because obviously they are not compact. That compactness I will discuss later in the session. So macroscopic scale holds when the number of particles is much greater than one. Okay, much greater than one means, so like it at least have to be, you can imagine, at least have to be, it depends on system to system, at least have to be 1,000 or more, right? So yes. Okay. So physics of water at millimeter scales. So physics of intergalactic medium on parsec scales. So I mentioned this term. So like fluid. So if I talk about fluid, I think if you distinguish fluid or astrophysical fluid, so it is termed as astrophysical fluid. Why it has termed as different word, right? So for our fluid, so we generally consider water, right? So the water molecules, I mean, the water molecules, if you think the density or their separation is much lesser than the astrophysical fluids. With astrophysics, we deal with parsec scales. I think some of you know about the parsec. So it is just a distance scale like kilometer, meter. It is just defined as 1 parsec is how much? So 1 parsec is 3 light year. Okay, at roughly 3 light year. It is defined as that. So it is like 3 times 10 to the power 16 meter. Okay, so this is the assumption of, sorry, here. So yeah, box of gas particles, microscope description we give from the function of velocity and position, right? So for a box of gas particles, we define their velocity or position, and we make laws for it, and we make a draw in their like 6 dimensional space, Fairy space, and those. So these are just some basic things I wanted to show you. So like fluid and solid. So difference between fluid and solid. So you know that fluid. Okay. So the fluid. So like if you give it a shear pressure, right? Shear pressure. So it will act like a viscous medium. So just imagine if you just trying to move a fluid just by rubbing your hand. So it won't be like that. Like for solid, if you like give a shear pressure, if it like a rubber, so it will have some elasticity, so it will give a response. Okay, and it will also give some resistance. If I like want to change its shape, it will show resistance, right? So that is for solid, but for fluid it doesn't show any resistance. This is for like normal general fluid. Okay, we haven't gone yet to astrophysical fluids. So this is for normal fluid. And you already have the lecture notes, but I am still showing you some basics. Fluid kinematics. So we know the streamlines. Okay, so like this is this line drawn is the path of the fluid. So you know, like imagine a river. So is flowing like this. So at any point, how its velocity is defined. So this is just for like any particle, but for fluid, it is more rigorous because like for solid, it tries to follow a direction. Uh, Normally, if it doesn't get affected, but fluid can flow through anything, right? Even like it doesn't go to straight line as solid objects. So its direction is defined as like here there is a head is the tangent of any point. So like the fluid is flowing, so at any point that its tangent is defined as the fluid direction. Okay, and the magnitude of it is about q, so the velocity is this q times u hat. more generally s hat is local direction. Okay, anyway, it's local direction, but all general. So you can't define a general velocity for a fluid, but if we get a lump sum of that, so somehow it gets defined, but it's not accurate. So, so if we try to define the ds, so ds is the uh whatever is called the minuscule length in x, y, and z. Okay, the it's so yeah, it defined as the dx is the infinitesimal length in x, and dy is in y, and dz in z. Okay, so and its velocity along those direction is ux, uy, uz. So the streamline is defined by this dx by ux is equal to dy by ui equal to dz by uz. This is how the streamline is defined. Okay, that that it's you can think it as like time, right? Because it is flowing as a whole, so the time it takes, so it will be the same, right? uh, at same time, like some on second time. So if it is moving in x dx and in y dy and in z dz with having the velocity ux, uy, ez, so the time is just you can divide with any of this, right? So the you can prove this very simple. Okay, you can try it out. If you have the lecture notes, you can see this is how this streamline is defined. So yeah, I already told us ds, dy, dz is the distance covered by the fluid along with these directions. Okay, it is recording now. The audio settings. Okay, okay, okay. No, okay. So then, uh, why is streamline ds defined as ds cross u is equal to 0? Can you tell? You must have read the vector cross product, dot product, right? So can you tell me why did ds cross u is 0? Anyone? First, tell me how the cross product of two vector, when the cross product of two vector becomes 0.
The quantity is conservative.
What? Can you be a little louder?
The quantity is conservative.
Yeah, the quantity is conservative, but yes, you are right. But here we are talking about just like small distance, right? So it's not like it have taken a like circular path or something. Okay, so if you're talking about
When angle
infinitesimal
is
length,
zero,
huh?
when angle between them is zero.
The end? What? Can you repeat again? Hello?
When the angle is zero,
When the sorry angle. Acha, you said angle. Okay, sorry. Yes, the when the angle is 0. Yes, you are right. So it means the velocity, the three-dimensional velocity you defined, and the ds is along the same direction, right? So that's why it is 0. Because I told you, so that's how the velocity is defined. And yeah, ds is called s is called the streamline. So yeah, it's basically the same direction. So that's why you're right. So okay, so these are the basic. I already told you that infinitesimal displacement is parallel to the velocity field. That was the answer to your question. Yeah, so it is parallel. So then the stream functions. The stream function goes as yeah. This is the curl of the the velocity is this curl of the stream function, okay, with a minus. And so yeah, so delta psi is equal to 0. So you can show this. These are just to to intricate you guys for some of those basics, so you can think. So then, yeah, so the stream function, if you want to show delta psi is equal to 0, so you can start with the velocity u from the stream function. Okay, so this is the, if you like break the curl, so you can show that u is like this, and we know that ds cross u is a 0, sorry, this is a null vector. So the ds cross q along z direction will be delta psi is equal to 0, right? So that's how we can prove. So yeah, so the stream function is basically conserved along streamline. So that is the important feature, that you said now, one of you said that it is conserved. So yes, so the conjunct property here is stream function. Okay, that is psi. So for irrotational flows, so irrotational flows mean there is no rotation, right? So if there is no rotation, so you know that curl of is 0, right? So yeah. So for irrotational flows like this, so we can define the velocity as minus grad of something, some function, some scalar quantity. So later we see what will be the scalar quantity. So now if I tell you that, so that grad psi dot grad grad phi is 0, so I think you understand how it can be done. So let me show you. So yeah, so that grad phi of x is basically this I delta y yeah, del y is mean, del y psi means actually del psi del y. Okay, so it is a notation, so to write in shortcut. So I think if you, any of you study Diracs or like tensors, you will see these notations very you will get this notation very friendly. So other who don't know, so del y is del y psi is del psi del y. Similarly, del xi is also same. So grad phi x is this and grad phi y is this. You can see from here, right? You can see from the above you. There should be some pointer. So the next class I will also use pointer so that you will get, yeah, yeah, we can do this here also. So okay, so yeah, and then this grad psi is also then we can get the grad psi is this, right? Grad psi is already there. So del x psi and del y psi for the x and y quantity. You can think from this normally that grad psi is with the usual directions. So these I think these are basically the Cauchy-Riemann functions that some of you that basically that normally taught in MSc first year, the Cauchy-Riemann equations. So that mainly deals about the complex things, complex mathematics, the complex numbers, that deals with complex numbers. So these are basically also Cauchy-Riemann equations. So then, okay. So from till now, I mean, you can let me know if you have any questions. How many of you think? Okay. because yeah, after this we will start some question answer session. uh, so till now you have completed the first week, no? Or you completed the first week? Okay. There is some zeroth week also. So those are some basic questions that you should take a look because that is also important. Just prerequisite for this course. So okay. So I told you about the stream function, the continuum, and the conservation of stream function till now. The other thing in the week on is flows, transgenic flows, and the okay, accretion disk is also there. Okay, reference material. Yeah, read upon the reference material. Okay, okay, and the other you got the lecture notes for week on, no? Or you have seen the videos. So useful. If you haven't, I can share the lecture week on PDF. Then I will get back to here. Not a problem. Because after this, the sample assignment problems. Okay, so just one thing. Yeah, I can use the pencil also. I think it will be good. You can't see the cursor, right? In the sharing screen. Yes, you don't. In that case, yeah. Wait, I have downloaded it, so I can. And where is the week on? There is some week on. Lecture notes. Yeah, but first the files. Okay. What is the week on? I just downloaded it. What? Oh, hmm. Okay. Now I'm sharing my screen again. There is some whiteboard features also. The problem is in that I can't open the document fully and the quality is getting reduced. Otherwise, I would just easily can open that in whiteboard. I will see. I think can be done the next session. So yeah, but yeah. So you have this, no, the modules for the lectures. Lecture one. So how many of you are interested in astrophysics? So yeah, I guess all of you are interested. Okay, good. So then this course is will be useful. So yeah, you have this, no, this
It's
different
7 o'clock.
1 o'clock. So it's astrophysics, bio, fluid. Yeah, there's some prerequisite for this: vectors, calculus, mechanics, kinetic theory of gas, electrodynamics, continuum hypothesis. I haven't repeated the same thing twice because you all know, I guess. You'll also be exposed to Euler, Navier-Stokes equations, Lagrange equations, and this is organization. Transonic flows. Acha, this is some just breakup. I think this is not much useful. Okay, this is not also useful. Leave it. These are for, I think, instructor. Okay. So now I think you can see the point. Yeah. So till now, I've discussed about these things, the macroscopic, microscopic, all this. So I think here is some space millimeter. So you can guess, right, the number density for solid and liquid. And so and gas, right? So the typical number density, I think you can calculate easily. So based on the size, so like from the density, like water density, uh, water density is on gram per centimeter cube, right? So in 1 centimeter cube it has 1 gram. Whereas if you take like iron, it will have, I don't know what is the density, but it is much more, right? It is much more dense. So the much denser it is, so uh, the much denser it is, so the much it has the atoms congested. So right, so that's how the solid and liquid are separated. Also, there are some other factors that's I already discussed, pressure and temperature. So till now, the streamlines and all. Do you have any questions? So you can tell me. Otherwise, we'll proceed to the question answer session and the assignment solutions. Um, And for astrophysical fluid, so actually astrophysical fluid is called fluid. Uh, so there are several places, like one is plasma, right? So plasma is very denser. So one scenario is for black holes, or like for binary quasars or pulsars. So their like jet is emitted like from AGNs, from active galactic nuclear, the continuous emission of jet. So jet is emitted, and the jet has the velocity. Jet has. Can you guess what is the velocity of the jet, astrophysical jet? Any one of you can guess what will be the jet velocity? On hint, I can give that it is very, very, very high speed. So it is moving in relativistic speed. So now, can you guess what is the velocity for astrophysical jets? If you guys are so silent, don't have to be that much silent. Don't worry. You can ask and you can interact with the sessions. Otherwise, I mean, it will be just I will talk and you will just listen. So yeah. If you are comfortable in chat, you can type in chat also. Not a problem.
Sir, can you please repeat your question?
Yeah, I'm asking that what will be the velocity? I mean, can you guess what is the velocity for astrophysical jets? So let me give you a picture. So like for AGN, so suppose this is a AGN, okay? Suppose this is an AGN. So AGNs, this is a central object, central galaxy, you can say. So from AGNs, so the jet is emitted, okay? Very highly relativistic jet outflow, okay? Very highly relativistic jet. These are called jets. These are very different types, so that if you go for PhD or master's project in astro, you'll get to know more. But so these are like jets, okay. So I'm not drawing exactly. So like for effort two, there will be some lobes. Basically, you can see that a quick outburst of things from region. So suppose like from black hole, so quick outburst of things emitted. Okay, so the materials flowing outside. So that is called astrophysical jet. So I asked you, like, can you tell me what is the speed? What is the typical speed for astrophysical jets? And I gave you two hints, like it is very, very high and it is very much relativistic, highly relativistic.
Can it be equal to or near to the speed of light?
Equal to near, you are saying equal to the speed of light or near to the speed of light?
Approximately near to the speed of light.
Yeah, you're right. So it is very, very high speed. It is like, okay, let me write in percentage. So it is have like 99.99% of the velocity of light. So can you imagine the velocity it has? So like we know that nothing can be faster than light, and the light can move the speed. it has and the speed of light, because the photons, the rest mass of photons are zero, right? So they are basically massless particles. But in the astrophysical jet, so they are basically fluids. The fluids in form of plasma. Okay, plasma fluid. So basically their mass is not zero. Okay, because they are fluids, but still they can channel into that much velocity. They can garner the velocity from the central engine this much up to this much. So it's strange, right? I mean, can you see? I mean, the accuracy, the speed it has. So, but from observation also, from observations, people find like for GW 17 or 1817. Okay, so that is a very uh, that is the yeah that is the jet flow from W77. For that, the Nobel Prize was given. You all know. I mean, you all keep track because I guess you all are physics students. So it has the superluminal velocity. Superluminal velocity. What is called superluminal? I'll tell you. Like 4c, 6c velocities it has. Can you see the velocity it has? Like 4 times the speed of light. So 6 times the speed of light. So you all know that nothing can move faster than the speed of light. But still, it has from the observation it has the speed of 4c. So it's simple, right? So how can you measure the speed of any object? So like the jet is flowing, so at one point, so suppose at one point it is here, okay, so at another point mt2 it is here, okay. So if you like just measure the distance among them with time, you will get the velocity, right? It's pretty simple. Like suppose it make the distance d, so the velocity it will have like d by t2 minus t1, right? So, and that is called superluminal velocity because that is our apparent velocity, but we are forgetting the space-time itself moving. Okay. So, but we can't consider that like from our observation. If we like, if you just want to observe, okay, suppose so now is the time of this planetary conjunction, okay, where the Venus, Mars, and all the Jupiter and sorry, not all Jupiter, Saturn are in a conjunction. So you can see the clear sky if your nearby areas are sky is clear, so you can see the conjunction. So yeah, so if you like observe through some telescope or something that how much it is moving with time, so you can get the velocity, right? So that simple velocity is called like this. But for obviously for jets you can't do in optical. Okay, if you're lucky you can, but normally the optical emission is not that much, so they are like emitting in radio. That is extended features. It only observed in radio. Okay, and the central accretion and all you can see in X-ray. So the point I am trying to say is that those astrophysical fluid, they are plasma fluids. So you can see they are channeled to that much high speed. So the study of this, the relativistic precision of it becomes very important for those scenario. Other fluid we also the astrophysics is also consider as a fluid, like there is this ICM, right? ICM, intercluster medium. So you can see the space is mainly empty. Okay, it seems very empty, but it is not. Like there are, it's. I mean, the number density of particles is very less. Suppose there's the number density of particles, so we already discovered Avogadro numbers and all. But for them, the number density is like one particle per centimeter cube. Okay, so like in 1 centimeter cube, so there is only one particle. Can you imagine? Whereas normal fluid, even for gas, if you measure the number density of gas molecules, you will see much more than this. In the at least in the order of 10 to the power 18 or something. So that you can figure it out. I give you exercise. I give you an exercise to derive the number density for solid, for liquid, and for gas. So take for some typical examples, okay? Like for 1 centimeter cube, okay? So you can define that. So that's where the study for astrophysical fluids becomes important because there are phenomena. So that plays role for different scenarios. Somewhere you can see, so everything like this is the intercluster medium is the medium between two clusters. Okay, so sorry, not two clusters, like the space inside the cluster. There is ISM, interstellar medium. So the medium between stars, like our solar system and the nearby Proxima Centauri uh, star. So the medium in between them. So that is also that is called ISM. So there is ICM, ISM. There is also IgM also. So there the particles density is very less. So that's where the study for astrophysical fluids becomes important because it plays the crucial role in defining those things. So yeah. So and all that. That's why this study for this fluid in astrophysics is important. Till now, I think in your lecture you haven't gone anything about astrophysics, but you will soon go because and I will be talking about more from astrophysical perspective because I am also doing research in astrophysics. So that's where my interest lies on. So and if you have any questions, you can ask me. Don't think like this is a very formal session. So you can ask any questions or any if we stuck anywhere. So we can ask the question. So do you have any questions for me or uh, otherwise we'll have to proceed. Okay, so the recording is stopped for some time. Saving recording. Hmm. Anyway, you can raise your hand or you can type in the chat box. You don't have any question. Any one of you have no questions? Yeah, Arti. Hello. Yeah.
Now I For now, I don't have any such questions.
Okay. Okay. So anyone else?
No, sir.
Okay. Okay. So then we'll proceed to the next section. So the sample assignment problems. So we have created some assignment problems for you. So uh, before we head to the assignment, the week on assignments, question answers. So I think it will be better if we discuss about these sample problems. So like, so first question is this: consider two identical containers. Okay, one is filled with oil and the other is filled with water. Wind is blowing horizontally over their surfaces. Which of the following statements are true? So you can imagine. So if I draw that these are two containers, right? Suppose this is container. There is oil, there is water. Okay. Okay, is there any lobby also, no? Is there any other waiting in the lobby? How can I see the lobby? People lobby, there is something lobby. Hello? Okay, yeah, there is another. Yeah. Okay. Lobby in the meeting. Okay. Hello to the new students. Acha, another thing, you don't have to like every time. I mean, I don't have to every time approve your request in the meeting, right? Or like if you like exit and then again re-enter, do you get this thing that I need to approve your entry? Okay, let me know if you face any difficulty joining or understanding the session. Even if you have problem in joining the session, let me know because this is the first time actually I'm teaching in Microsoft Teams. Earlier I used to do like Google Meet and Zoom. So this Microsoft Teams is new to me, but it is very effective in my sense. Like recording and all, and document sharing or the file sharing, for that it is very good. And our institute has got the Zoom, so that's why this Teams thing is new for me. New in the sense like for teaching in new, but when I was a student like you, so I've also joined classes and meetings in Teams. Okay, so the new students, if you have any problem, let me know. So we just started doing the assignment problems. Okay, so the rest of the part, the session is being recorded, so don't worry. So it will be shared with you all, and it will be uploaded in the YouTube, and you can see, I mean, what we have discussed and what doubts. Yeah, thanks. Okay, okay, yeah, this says it's okay, and another person has joined, but okay. So my voice is clear now. It is like yeah, quite. It's not that much. If I can increase the sound if you want. If it is voice is okay now, loud and clear. Thank you. So this is the first questions you can read. So two identical containers. So there is one oil. I think I need to draw with another color. No, water is blue, no? So try blue. Not blue, sorry. I ocean water like. So this is water. I got amazed how people can write so clearly, even with pencil. But my handwriting is okay. Anyway, so the wind is blowing. Okay, the wind, the color of the wind. So suppose the color is there is no wind color, but suppose it's a mist. Okay, so then they will have this white foggy thing. But anyway, let me just draw with blue only. So the wind is flowing over the surface. Okay, the wind is blowing over the surface. So okay, so this is the picture. Okay, so then which of these statements are true? Okay, that first option is the horizontal component of velocity of the oil at the very bottom of the container will be zero. Okay, so the first option is yeah, the horizontal velocity for the oil will be zero. So that means that the wind is not moving. The not moving. It is not. It is obviously. So if the wind is flowing over the surface, so they will move, right? Because they are liquid, so they will move. But the first option is that the bottom of the oil, the molecules, the liquid in the bottom. So for oils, the oil in the bottom is not moving. Okay, that means that it is not moving. It is not moving. So that is the first option. Second option is the vertical gradients of the horizontal component of the flow velocity will be the same for water and oil. So second option is it is saying that okay, it will move. Okay, it will move. So the horizontal component, so it will move, but the vertical gradient. So there are layers, right? There are layers in. So these are the layers. These are the layers for oil and water. So the layers are moving, right? But between two layers, suppose the between two layers, so the speed won't be the same, right? Because you must have read the viscosity thing, right? So these are viscous medium. So the difference between oil and water is, oil is more viscous than water. So more viscous means, so between two layers, so it will repel the motion. Okay, it will repel the motion. The lower ones won't move that much as the upper ones. Okay, because it will repel the motion more. For water, it is also repel, but it is not. It won't repel that much. So that is called viscosity. Okay, that depends basically about the density, the velocity gradient, or temperature is also there. Uh, I can't recall the exact what the exact equation for the viscosity to measure. So depends something on the length scale and the real numbers, right? So that is depend on the viscosity is eta. What are the expression eta? So there is velocity, na VL by eta. Okay, anyway, VL by D something. Okay, VL by D something. I think different expression. So anyway, that is not the purpose of the problem. So the thing is, so this is the vertical gradient. So it is saying the vertical gradient will be the same for water and oil. So it is not, obviously, right? Because oil is more viscous, so you can easily neglect this option. The third option is the horizontal component of velocity of the oil at the very bottom of the oil container will be the same as the horizontal component of velocity of water at the very bottom of the water tank. So it is saying that the horizontal component at the bottom of the water and the bottom of the oil will be the same. That is basically an extension of the first questions. Sorry, first option. Last option is the horizontal velocity component of water at the surface will be the same as the horizontal velocity component of oil at the surface. The last option is it is again saying the horizontal velocity of oil and water at the surface will be same. Okay, here surface, this is the bottom. Okay. Now these questions are for you, so it won't be fair if I just give the answers directly. You have to tell me what should be the answer, right? Only that it will be fair. Don't worry, these are just sample questions, so you can just think and yeah. So who can tell the answer? What will be the right options? I already tell you the B can't be the right answer, right? And also D also can't be right because D is like the surface velocity for oil and water will be the same, but it's not right. Just imagine mercury, not mercury, sorry, oil. Just imagine a oil, a bottle of oil, not bottle, container of oil and water. So the air affects more water, right, than oil because oil is more dense. I mean, normally if you think like in layman terms, so oil is more dense, it is very denser, but water is not denser, it can flow. So the last option can't be right because
Option
so
C.
what?
C.
Uh, Sorry, are you saying something? Saying something, Arti? Yeah.
Option C.
Acha, you are saying option C. Okay. Why? Why you think the option C? Arti is saying the option C. Sorry. Sorry. Yeah, sorry. Why are you saying
So,
it?
Sir, I don't know the answer.
Okay. Yeah, but you can
so
guess, right? I mean, normally just think terms of oil and water.
So you said B and D can't be the answer, so I have the option of first and the third one, that is A and C. For the first one, that it says that the horizontal component of velocity of the oil at the very bottom of the container will be zero, right?
Yeah.
But it is also mentioned in the question that is wind is blowing horizontally over their surface. So if the wind blows, it means that there might be a certain amount of water or the velocity or the oil that will be displaced, or it will move at least. Okay, so vertical component, there won't be any vertical component that is making the water or the oil to move, but there might be a horizontal component that is the reason why the oil particles or the water molecules move. So it can't be zero according to me. So I'm left with option C, that the horizontal component of velocity of the oil at the very bottom of the oil container will be same as the horizontal component of velocity of water at the very bottom of the water tank.
Okay.
Because we can also say that because the wind is moving on the surface, right, and the container is closed from three sides, bottom and the other two sides. So at the bottom of the container, the velocity of the oil might be same as that of water because they aren't moving at all.
You are saying that the bottom of the fluids are not moving. The bottom molecules are not moving, right?
Mm, yeah, maybe.
That is basically option A, na? That,
Yes.
yeah.
Yes.
So you're right. I thought you take a 50-50 chance that okay, I'm left with A and C, so I'll just go. But what you didn't know that both are right actually, A and C. Okay. So the
Yes.
yeah. So the thing is actually for solid because this is a container, right? So this is a solid container. So so for solid container, okay, the horizontal component of the fluid velocity at bottom, okay, for in the solid surface is always zero. Okay, it's always zero. Zero. Velocity is zero. Okay,
Okay.
that's the thing. Nothing else. It's zero. Whether it is oil or water, it is zero. First option it is only mentioned oil, but if you go to the third option, so the horizontal component is same for the oil and the water. So means for water it is also zero, right? So because this is a solid surface, so it must be zero. And also, yeah, it also zero. So basically, A and C tell the same thing. So A and C are the right options. So you're right. 10 points to Arti. So, but others, please also interact during the session. It will also be good if you interact. You'll also get to know, and I will also get to know from you. I mean, from your perspective, I mean, uh, how you are reaching to the answer, right? That is also important because it's not just about telling the answer, right? It is how you approach, how you think. Okay, that also matters. Okay, but if it said like these are not in container, like oil and water not in container. Suppose a ocean, suppose an ocean. Okay, so obviously the very bottom of it. Okay, for ocean also the very bottom of it is also solid, right? But there is not like zero. There's some various phenomena happens because of the vorticity and all. You must have heard of the Mariana Trench and all. So I mean, because of the saddle points, and so those kind of there is some vorticity and basically there is some turbulence occurs. So that is some complex system. Turbulence is fluid also deals with turbulence. Okay, it's not the turbulence is out of the scope. It's not turbulence. You can also define turbulence because turbulent motions is also depend on the initial conditions, and they can be categorized in like okay, I don't know whether if you are hard or not. So there is like so mainly before turbulence, we call like instability. Okay, suppose system is unstable. Okay, it's moving instably. Then suppose some instability occurs. Okay, like some uh, like some like it tackles into some obstacles, okay, and something happened. So that is called instability, right? So there are several instability like Kelvin, Kelvin Helmholtz instability. Okay, I think that will be in the later in the course. Okay, so Rayleigh instability is also one thing. So they also define these kind of things like vertical motion and horizontal motions. So yeah, so that is the one thing I wanted to say. So then yeah, so A and C, yeah. Then we head on to the next question. Okay, so this is it. Yeah, up to this point. So this is question number 2. So consider a horizontal pipe AB with water is flowing from end A to end B. The flow speed is well below the sound speed. So basically, it's a subsonic fluid, right? Subsonic, you know, na? Subsonic. Subsonic is when velocity is less than the velocity of the sound, and supersonic is when the velocity is greater than the speed of uh, sound, right? And there is some ultrasonic also, which is the velocity is much greater than the speed of sound with very high Mach number. But yeah, we are dealing here with subsonic fluid, so that the flow can be considered incompressible. Okay, the flow speed will below the sound speed. Yeah, so yeah, actually, so we said na the fluid is incompressible or compressible. So uh, the compressibility is defined with the nature that basically the compressibility deals with the Mach number. Okay, the Mach number. So there is a Mach number thing. So Mach number is defined as uh, V by Vs. Okay. And there is some compressibility parameters also, like jump parameters and all. So the compressibility depends on the Mach number. Okay. Like if something has very high Mach number, okay, then it can't be it can't remain incompressible. Okay. So and anything it can compress the fluid. Okay. There are some other factors also, like if the fluid is itself, in some enlarged state, like you see some jelly or thing, if you press it, it is compressed. Okay. So here we are dealing with incompressible fluid. The cross-sectional area of the pipe is gradually increasing from A to B. Okay, the cross-sectional area. So suppose this is a pipe. That's why I haven't drawn it. So this is a pipe. Okay. This is the end pipe. Their cross section is gradually increasing. Okay, so it is becoming more and more. It is becoming more and more. Okay, so this is some pipe. This is pipe. This is A. This is B. Okay, and this is water. Water is flowing in this direction. This is filled with water. Okay, this is filled in this direction. So tell me what will be the correct statement. Option A is pressure at end A. So pressure here. Okay, and pressure here. Pressure at end A less than pressure at end B. Option B is velocity of water at end A is velocity of water at end B. Also, pressure is there, velocity is there. Option C, the amount of water near end A is less than the amount of water near end B. Sorry, option B is greater, no? It is greater. Okay. And option D, the density of water will vary with cross section of the pipe. Okay. Option D tells that the density of water will vary with the cross section. So basically, if I write it mathematically, so it is actually PA less than PB, VA greater than VB. The amount can be defined as mass, right? Because this is incompressible, so density is same everywhere. So the amount basically the mass. You can think about the mass because mass is equal to what is mass? Yeah, yeah. volume times density, right? So the mass is total mass. Okay, the total mass. So write is ma. And then the density of water will vary with the cross section of the pipe. Oh, sorry, I already told you incompressible, so it can't vary. So density is varying with the cross section. Okay. So tell me, what will be the right answer for this one?
Either A or B will be the answer. C cannot be the answer. 90% I'm sure that C won't be the answer. And D will not be the answer because the density of the water density is a property of the substance. So density is mass over volume at a standard temperature and pressure. So D will not be the answer. And for C, I guess 90% it won't be the answer. So either from A or B, the answer is correct.
Acha, you are so confident about option C that it can't be the answer. Can you tell why it has the right probability only 0.1?
It is because I don't have a scientific answer to it. It's just the assumption that suppose I open the tap, okay? So the
Hmm.
water is, so if I consider this as a water pipe and at the end B I have the tap. So if I open the amount of water that will flow from A and that will be the equal of amount of water that will fall from B, right?
Okay, but but think here this area is less and area is more here. The area is more at B,
Sir,
But
I
right?
the
think it's
water will
B.
start to be, but the water will start to enter from A, right? It will not go from B
Yeah,
to A. A water is going from A to B. So suppose that if 1 liter water is flowing from A, then it means that the 1 liter of water will also flow from B. It won't increase on its
yeah.
own.
Obviously, it won't increase. No, it's like the water is flowing continuously. Okay, the water is flowing continuously. There is already all the time there is increasing water. There is outgoing water. Now, do you think that you will change your answer?
Sir, I think
Let
it implies
Huh?
conservation of mass.
Conservation of
Conservation of
mass.
mass.
But this is not a
I think I
conserved system,
agree
right?
with
This is
conservation of mass. That's why it shouldn't be number C.
yeah, I understand you are thinking about the conservation of mass perspective, but this is not a conserved system. This is a continuous system. The water is coming to point A and this is flowing. It is getting out from point B.
so
Sir,
but still
divergence
I
should be zero.
would but I would still agree that C won't be the answer.
Okay, okay, let me tell you like this. Okay, what can I say? Like there you have a bottle. Okay, you have a bottle.
Hmm.
Okay, and this side, this is the bottle mouth. Okay, this is the bottle mouth. This is the bottle end. And you suppose you just open the bottle and you cut the bottle bottom. Okay, so just at a snapshot, at a screenshot. So uh, what will be the water remains at the bottle front and the bottle bottom? Which one will be more?
Bottom, sir.
Sir, B.
Bottom, right? So it's simply that. It is simply that there will be more water
Option C is
near,
correct.
yeah, near B, but there will be less water at point A. Okay.
What if we
See,
tilt the water bottle into horizontal? Instead of holding it vertical, just tilt it into horizontal. You will
it
see
is a
that the
horizontal.
amount of,
See, it is the horizontal. Consider a horizontal pipe.
but still I would say that C can't be the answer. I would go with B rather, that B can be the answer because the flow of water will adjust itself. But
Acha, B, what B says that the uh, velocity will be more at point A than the point B, right?
mm, yeah.
Why? Why? Because you said that the conservation. Okay, at any point the conservation. And what is the conservation? That this cross section here, right? Cross section, yeah.
Hmm.
That a V times A, right? It should be constant.
Yes. Area
Okay,
times velocity.
yeah.
Hmm.
So VA, AA, VB, AB, but AA is less than AB, right? So basically, it's like this: VA by VB is equal to AB by AA, and AB is more than
Hmm.
AA, so it is greater
Yes,
than
sir.
1. So VA greater than VB, right? I told you very simply, very simply, but really I think you solved the moment equation in Maxwell, right? So that I think in the course, right? So the for fluid the equations. So a simple picture is VH constant. So B is, yeah, B is right. C is also, yeah, C is also right. So both
So,
B, yes, yes.
sir, so according to the equation that you wrote, uh, can't we just conclude that at the narrower point, that is at A, the water will be flowing faster, whereas at the B, that is the wider end, the velocity of water will be less. That is the option B, and which is right. So according to that, if we look at the C, so doesn't it mean that if the water is flowing more with a higher velocity at A, so it means that there will be more and more water coming at that end faster. Whereas at the B end, it will be velocity of water is lower. Okay,
Yeah.
so doesn't it mean that the amount would still be the same at both the ends?
No, 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 no. Okay. Listen, we haven't talked about anything pressure, right? We haven't talked about pressure here, right? So you are thinking this
Yes.
perspective, like more water is coming from this, but but when it is exiting, it won't cover that much. You're thinking like that, na? but but
Hmm.
don't think like that. Okay, so think, just think in the terms like, okay, water is flowing but it is gradually increasing, it is not like very much increase. So nothing is told about the viscosity and pressure and the how much it has increased at point B. It is only say that it is gradually increasing. But suppose the water is flowing, okay, the water is gaining. So what happens, like, if you think about our artery, the arteries are
Hmm.
in our body. So the blood is flowing, right? Blood is flowing. So when the blood is flowing, so what happens when, in some point at artery, when it large, na, when the artery radius is large, okay, the cross section, radius means your cross section large. So it is not like they won't flow from that point. They will flow from the whole cross section, okay. Suppose, but
Yes.
otherwise we won't get any blood in our body, I mean, in our head, right? So you are right. You are thinking about the pressure point of view. Okay, suppose the pressure is not that much, fluid is flowing and it is just moving. But here something is channeling the fluid, right? And obviously there is no gravity, so gravity is already not in the picture. Okay,
Okay.
but still it can be some force, right, that is channeling the flow, okay. And when it takes like a more cross section, so it will obviously flow from the more cross section. In practical, you may have seen in the duct pipes and all that, okay, it hasn't flow from the whole thing. Obviously it will be more in the lower side, but that is due to just gravity, okay. But if you gravity or like some air pressure or viscosity is also there. But suppose the on end is full, it is flowing from full, okay, then in other end, so quantitatively there will be more fluid, na, more liquid, more water at this point, because it's at the more cross section. So if you think like mathematically, so mass, that I told you, density times volume, okay, mass is density times
Density
volume.
times volume.
Density is same, volume is more here, more volume is here. Example, if I,
Okay.
yeah, it is said near, na, so if I take like 1 centimeter length, so then m proportional to a,
Eh,
yeah. So Both B and C are correct. I mean, what the point of the perspective of yours is not wrong. It is okay. It is right. But the thing is, nothing is talked about. Nothing is talked about the pressure and other conditions. It's just normal picture. So in normal picture, okay. So this will be the case. If you think mathematically, so yeah, m proportional to a, and this is also there. Okay. So, but if you do look more rigorous mathematics, so then yeah,
Sir, can you repeat B part, velocity part?
huh?
Can you please repeat velocity part? I don't get it.
Yeah, velocity. Yeah. Okay. So VA is constant, right? Velocity times area is constant. Hello.
Yes, sir, I'm listening. I'm listening.
Okay. What are the name of the law? So what it is called? It's just the conservation of it's just the conservation. Okay. At any
Silver
point, the
knowledge
velocity
theorem,
times
maybe.
cross section will be constant. So the velocity at point A and the velocity at point B, okay, and the area, the cross-sectional area, hello,
Yes, sir. Yes, sir.
yeah, and the cross-sectional area at point A is less than the cross-sectional area at point B,
Yes, sir.
okay. So then if VA is constant, so VA is the velocity at point A, AA
Yes,
is
sir.
the area at point A, and VB is the velocity at point B, and AB is the area at point B. So then VA by VB, mathematically VA by VB is equal to AB by AA, and AB is more than AA, so it is greater than 1. So then VA greater than VB, right?
Yes, sir.
Yeah.
Yes, sir.
Mm-hmm. Uh, okay. I've prepared it, but the thing is, but you're right. Actually, now I thought of it. I also write these things earlier, but yeah. Actually, about the C. So, if no other conditions are mentioned, okay, it will also be the answer. But okay, if the some conditions are imposed, like I have written when I have prepared this. So when some properties are mentioned, so yeah, like the other factor, like you told practically. So then C may not be the answer every time. Okay, the C is not obvious. Property of C is not obvious. That's why I have written somewhere that only B actually. But hmm. But that time C about C it is not mentioned anything. There is no root density. Yeah,
Sir, if we assume like two of the factors, that one
hmm.
being that the fluid is incompressible, and
Hmm.
the second being that the fluid occupies the whole cross section,
Yeah.
then won't this to be enough to say that C is true?
Yeah. From that perspective, yeah, yeah, you're right. From that perspective, I also told that, yeah, it will be the answer. So,
Okay.
yes, you're right. So, but it is not, I mean, obvious every time because the pressure is not mentioned that much. Uh, so if you inverse the scenario, if you inverse the scenario from like more cross-sectional area to less cross-sectional area, okay. So, yeah, more cross-sectional area to less cross-sectional area. So, what will happen? So there the pressure thing will come, right? It is not the same actual. It is not actually the same as this situation. If in the situation, it will be more chaotic, right? Like from more to less. But again, it deals about the pressure also. Okay. But
Sir, what is official answer for this question?
I don't know. This is sample problems. There, yeah, the answer we have written as B, but there is nothing as uh, official answer. Okay, don't think. I mean,
Sir, I
should be
think
some. There should be
cross-sectional
only on.
area means.
Huh?
Sir, I think cross-sectional area means when we cut a small part of the actual system to a small system. I think that the area will be limited to that small limit. So option C may be correct.
Yeah, yeah. Cross section is basically area. I mean, what it is called? Crossed. Again, I am just referring the same name. Crossed area. Okay, projection. Suppose it's some projection. Okay.
Is it finite or it will be infinite? So I
No,
think it will be finite.
nothing is said about that. No, nothing is said about that. But you can use your imagination, obviously. Like if you see that only here, only about B is mentioned and D about mentioned. Okay. And pressure can't be less than pressure at point A can't be less than pressure at point B, because we know that normally that pressure is water is flowing from high to low pressure, right? Otherwise, the first thing it will do that it will move. That's the thing. So actually, yeah, Arti was somewhat right, thinking that okay, it may not be. But yeah, that's the thing. There is no official answer. I mean, to any question. I mean, often see like so many questions, the answer are given wrong. I mean, somewhat typical spelling mistake, or but some are more like more rigorous thinking can be done at those point, right? So yeah, without further ado, we'll move to the next question, okay? Otherwise, we won't finish. So, any questions in that?
No.
Okay, so let's move to the next question, right? I have added the two slides. Yeah. So the next one is, yeah. Consider the velocity distribution function of a Maxwellian gas. Okay. In order to compute the pressure of the gas, one needs to know. So it is about the velocity distribution function. Yeah, you know the velocity distribution function of Maxwellian gas, right? So do any of you remember the expression velocity distribution? What it is? It is just a times a to the power minus mv square by kt, na? So m by 2 pi kt. So bv square, or there is dv, na? mv dv. Okay. So consider the velocity distribution. Yeah, they a and b have this usual constant. I think a is uh, there is some a cube also. No, no, no. If you think just 2 pi, what are the 2 pi m by kt, something, no? To the power 3 by 2. B is also uh, 2 kt by m. So m by 2 kt, something. Yeah. So basically, this is the expression for Maxwellian velocity distribution. In order to compute the pressure of the gas, one needs to know. So if you want to compute the pressure, what you need to know? The first moment of the velocity distribution function, second moment of the velocity distribution function, the zeroth moment of the velocity distribution function, or the entropy of the gas. Tell me. What will be the right option? Sorry, right option for this one. First moment, second moment, zeroth moment, or the entropy.
Sir, I think it's B.
So you're saying B? Why?
Yes, sir.
Why?
Sir, I don't remember, but I have seen this in video. It was B.
Huh?
Sir, I don't actually remember now, but I think it was B.
Okay, acha, acha. The second moment. So basically, yeah, you're right. B is one of the right answers. Okay. The reason being is the second moment of base distribution function. It talks about the temperature, kinetic energy of the gas molecules. Okay. So yeah. The second moment of the velocity distribution function talks about the kinetic energy, and we know the kinetic energy of any distribution, mainly velocity distribution, or I mean the kinetic energy. So basically, kinetic. What is kinetic energy? So if you think about individually any particle kinetic energy, you know that expression half mv square. Okay, but this half mv square, this is like in on degree of freedom. So the kinetic energy of that particle, it basically refers to the temperature of the system, right? So the second moment of velocity distribution function talks about the temperature. Okay, it talks about the temperature here. So uh, and also we also need to know the third one, the sorry, the zeroth moment of the distribution function also, because the zeroth moment, this is the second moment. There is also zeroth moment. Okay, the zeroth moment talked about the number density.
It's 8 o'clock.
It's number density. Okay, and we need to compute the pressure. So can you anyone tell me what is the expression for pressure? Hello.
Sir,
So
I
how
haven't studied about this topic yet, so I'm not really familiar with this.
you haven't talked about this topic? I think. Okay, don't worry. I think then it's my
I'm
fault. I have.
No, I'm talking about my curriculum that I have.
Okay, okay,
I don't know about this course, but for
okay,
now,
okay.
because I'm just in second year, I'm not familiar with this
Okay,
topic.
okay. Yeah, because the time when we have arranged these all, okay, this question answers, okay. Okay, so first thing, I haven't done this all by myself. Okay, we have the team, so we have done this. Okay, we with the professor and uh, other TAs also. So when we prepared this, so based on the uh, week weekly content, so we incorporated the things. Okay, so, but yeah, obviously some points may seems like ad hoc, okay? Because now like I also have, I also get the full course. So when you like complete the full thing, na, you sometimes on thing you think like okay, it is the first week, but it may or may not be that much, because you may have, yeah, these things happens when you like, even if you when you complete the whole course this time, and if you complete the course fully, so you'll also think okay, in which week I have studied. So those kind of thing comes. So basically the pressure is related, okay, the pressure is related to the temperature and the number density as, sorry, as nkt. This is basically the, what is the called, the ideal gas law. Okay, what is ideal gas law? Ideal gas law is this, na, that pv is equal to uh, inerty, right? Pv is equal to inerty, we say, right? That you
Yes,
have,
sir.
yeah, pv is equal to inerty. So but here n is different. This n is mole. This n is mole. Okay, or sorry, so here the n is mole, and r, how r is defined. Uh r is, sorry, uh, yeah, this Boltzmann constant defined as r by na, right? This r is,
Ye-
what is it called, molar gas constant.
Redbird constant.
Huh?
Avogadro constant.
And na is
Redbird's
the,
constant.
sorry, what?
Redbird's constant.
Yeah, Rydberg constant. I forgot the name. It's long time. I also like normally we don't deal after HS, we don't deal with R anymore, right? We mainly deal with K. But yeah, this is Rydberg constant. So K is equal to R by Na. So if you like put it here, so what will you get? R is equal to Kna n Na kt. Na total number, right? So this will become basically nkt. So PV is equal to nkt. Then if you do like P n by V kt. So this n by V is number density, right? In a volume V, what is the total number? So this is basically nkt. This nkt, this n is different. Okay, don't get confused. This is the mole that you studied in your high school, but this is now the number density. It has the unit of per centimeter cube or per meter cube. Okay, this is important. We now deal with only this n number in every scenario. Normally, when talks about fluids, or even when you talk about in astrophysics, mainly when you talk about the hydrogen column density, okay, or yeah, for plasma. So we mainly this terms becomes important for simulations also. We use this small n. So that's how the p equal to n terms come. So try to remember this equation. It is very much useful. So yeah. So p is equal to nkt. So from second moment of inertia we get the temperature. From the zeroth on we get the number density. So that's how p becomes nkt, right? So that's how we can compute the pressure. So it's option B and C. So yeah. Any question?
Uh, yeah, so we know this for the Maxwellian gas, this distribution, it's like a what do we call? It's like a normal distribution, right? Like a Gaussian.
This is
Then,
yeah, this is Maxwell distribution you're talking about, no? Yeah, it is
mhm.
not it the same. Huh.
And when we talk about like first moment or the second moment, like the first moment
There
in
is some
this
other
case
term,
is
no? There is some here. There is some V square also, no? Statively, I think. Yeah. Say.
oh okay, then it won't be a Gaussian anymore. Okay. No, then so I was just asking like uh, maybe without using the equation, just by knowing the graph and
Uh,
the idea of first and second moment, like can we then derive or like can we then solve this question?
yeah, you need to compute the pressure, right? So
Mhm.
obviously for pressure you need the number density and you need the temperature, right? So from velocity also, obviously the temperature comes from the velocity, right? So if you like from the plot, if you take the Maxwellian velocity, okay, so you get the what is it called maximum probable velocity, right? uh, Vm, that is defined as root over 2 kt by m, right? So if you get that, you will
Okay.
get the temperature. You'll get the temperature, okay, and the number density you will also get from like the distribution functions, other equation like from A. Okay, but the here you're right, but it's not like you can't get the answer from any other thing. It's just the I mean from these options which are correct. Okay, it's not
Yeah,
that the
okay,
only
understood.
possibility. It is about just the I mean okay, obviously you can determine from the graph, but that is not in the option, right? If I say like that, it is just wanted to know that you particularly remember which moment talks about what, right? So basically that. Any other question? I think I have only 20 minutes, 20 or 15 minutes. Okay. Any question? I think we have another two questions. Then we need to also solve the previous week assignments also, no? I think. Okay. Yeah, so let's head on to the next questions. Yeah, that we already have discussed. Okay. So the question number 4. Suppose you have two gas containers A and B. Container A is cylindrical with a radius of 5 centimeter and height of 10 centimeter. Okay. Total number of gas molecules inside container A is 2500. Container B is spherical with a radius of r is equal to 8 centimeter and is filled with 3500 molecules of the same gas. Now consider an imaginary cube V of length on centimeter well inside each container. Okay. So yeah, two gas containers. Consider container A is cylindrical. Okay. So it is cylinder. Um, Container A is basically a cylinder. R R is 5 centimeter. L is 10 centimeter. So inside total number is also mentioned. Container B is like that. A little more radius. Let me do one thing. I think I can. Yeah. It is a little more disconnected here. It looks more good, right? Ah, this is 8 centimeter R. So more molecules. Now consider an imaginary cube of length length L on centimeter well inside. Acha, just a cube, okay, just a cube. Just imagine a cube of 1 centimeter. So then what are the options? One can consider the gas inside V of container A as a fluid. You can read it, right? So yeah, tell me what will be the right answer. What is that? Okay. Anyway. So can anyone tell me what which option is the correct? Hello? If you need time, so you can take, I think. Basically, it is said that you can consider this 1 centimeter cube, the molecules inside 1 centimeter cube, we can consider them as fluid. Okay, that's the question. We say that they are gas molecules, but the options are saying basically A, B, C all are saying that the gas molecules inside this 1 centimeter cube we can consider them as fluid. Okay, there is some like existential questions for for liquid and gas. So the question is, can we consider them as fluid? So what parameter defines that? You can think from that perspective.
Sir, as far as I know, like fluid itself is defined as either gas or liquid, right?
No,
So
no, 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 no. Yeah, you are right. Fluid, no, no. What did you say? Fluid is considered gas.
no, I mean, If you have either gas or liquid, then those come under fluids, right?
Gas you can consider, yeah, gas you can consider fluid, yeah, but that is, I mean, you can consider, but it is not like, okay. So,
I
those,
think we have
listen,
to
so you
check the
can't just say
definition.
that, okay, I told gas molecules, then for 1 centimeter cube, you can consider also that fluid. I mean, there is some, what, there's some intriguing thing, na? I mean, what parameter you said, right? In that, yeah, in that sense, yeah, obviously, I mean, uh, we consider, like in cosmology, we consider the whole universe as fluid, right? The stars, the galaxy, they are fluid, and they are like flowing in a container, like Rasgulla, na Rasgulla. Yeah. So it's like the cosmological people consider that the whole universe is like a container of Rasgulla. Okay, and the Rasgullas are moving or flowing. Okay, in that Rasgulla fluid, that liquid. Okay, what happened? You understand, na? So that's how they define. Okay, but it's not that, right? I mean, you can't just tell from the fact. Okay, I think due to the charge, someone is joining now. Yeah, hello. Can you hear me?
Yes, sir.
Yeah, yeah. So basically, the parameter, you have studied this, what it's called. I also forgot the name. Uh, continuum system, right? Continuum system. The first thing, remember, 24, 24. Yeah. Continuum, continuum
Yes,
limit.
sir. Yes, sir.
The continuum limit, right? The continuum limit. Yeah. It holds good when n is much greater than 1, right? Huh?
Okay.
But also there is one condition other, na, it is something may have missed, but another condition is n L cube much should be much greater than 1, right? Okay, sorry, it's mentioned actually. Yeah, n is what? N is n L cube, right? Sorry, this is capital N. N is L cube, right? Hello?
Yes, sir. Yes,
Yes.
sir. Yes, sir.
Yeah, yeah. N is N L cube, na? Okay. Where I was at. So the condition is, sorry, we'll say that. Yeah. The condition is n should be much greater than 1, na? So what is n? N is total number. So number density times volume, right? So it should be much greater than 1. And here L cube is 1, right? Here L cube is 1. So the condition should be n much greater than 1. Now just calculate the n. No? Now just calculate the n for each of these case. Okay. So what will be the n? What are the space? Okay. So for this one, number density, the equation is total number of gas molecules is n divided by what? Uh, Cylinder's volume. What is the cylindrical volume? Is pi r square h, right? Volume for a cylinder is pi r square h, right? So the volume
Yes.
is pi r a square L a. So what is that? Just compute. I need to hurry a little bit. 2500 divided by pi. Ra is 5 centimeter. So 25. La is how much? 10 centimeter. 10 centimeter, no? Yeah. Uh, yeah, 10 centimeter. So what will be this? So 10 cancel, 25, 10 by pi. So that is at most 3, right? Na is 3. Nb is again 3500 divided by pi. Now R is 8, so 64. What is the L here? Total number of. I think L is same, no? L is same. So now 64 divided 350 divided by
No,
64.
it's
So
a sphere. So we have
Sir,
8 cube.
container B is a
R
sphere.
cube.
oh, sorry. Quantum B sphere. So what is the sphere volume for third? What is the volume for the
4 by 3 pi r square h.
what?
4 by 3 pi r square h. Volume of sphere.
Pi R cube, right?
4 by 3 pi r
Yes, R
cube.
cube.
4/3 pi r square h.
For
4
sphere
divided
there
by
is
3 pi r square h, right?
for sphere there is no height, right? There is only radius.
Oh yeah, 4 by 3 pi r cube.
Yeah. So yeah. So and what is R? R is 8, right? So then
Yes.
okay, so the 3 will go here. So it will be 10,500 divided by pi times, sorry, 4 pi. R is how much? 8. So 8 cube is 256. So then if you divide that, how much you will get? How much you will get? 4 times 256 is 100, 100 by 10,000. So again it is like 3.5 something. Just calculate. I just roughly it will be like 3.5. So both the cases, okay, both the cases, n is greater than 1, not uh, not much greater than 1, right? It is not. It is not much greater than 1. It is quite the you understand, na? Much greater than 1 means it has to be like a large number, at least I told you initially, like 1,000 or something, right? So, but these are just number 3. 3 is nothing but I mean if you compare with 1,000 and all, so 3 is like on. Okay, 1 to 3. Very just greater than 1, not like much greater than 1. So it doesn't fall in the continuum limit. So nothing, it can't be the answer. So all the above statements are false. Okay. So this is the correct answer. Okay. Understand now?
Yes, sir.
So now let's move on to the next questions. Last question, last sample question. So consider a two-dimensional flow with the x and y components of velocity given by ux is this, uy is this. Pick all the statements which are correct. Okay. So, acha, you remember the Cauchy-Riemann equation, na? So think from that perspective. What will be the correct answer? Flow which is radially converging. This describes a flow which is radially diverging. Flow which is rotating in the clockwise. Okay. Tell me. Which one should be the right answer? So you know, na, somewhere I told you that it is a irrotational flow, right? I said where irrotational flow. Irrotational flow, na? Curl of u is 0. Irrotational
Uh,
flow means curl of u is 0, right? Curl of
Yes.
curl of u is 0. So if curl of u is 0, So obviously C and D are wrong, clearly.
I think it's radially converging, option A.
Okay, but how? How you can say that?
Um, so one way, like I did some maths. What I did is x square plus y square. I can just take it as r square, and xy I can say as r cos theta, r sin theta, and then I just differentiated them with respect to r. So that's del ux by del r, and that will give something like sine theta into 1 by r square. So as r goes from 0 to say infinity, then it tends to 0, right? So it's converging.
What can repeat for?
Okay. Now after this, we can differentiate it with respect to r. So it's like dux by dr, and
You
that
want
will give
to?
like
Okay.
uh, actually more precisely the what we call the partial derivative with respect to r. Yeah, so
Oh yeah,
that
yeah. There
gives
are
cos
theta, na?
theta
There
by
is
r
theta.
square.
Yes, yes, yes. There is theta. I should write, yeah, in the partial form. Yeah.
Mm. And same for the other one. So like
Same
we
for.
have cos theta by r square. So this 1 by r square dependency. So
Yeah.
as r goes to infinity, this goes to 0, right? So it's converging.
Wait a minute. You are saying, or acha, you're saying from at r is equal to infinity, r tends to infinity, it is zero, right?
Yes, yes.
Okay. But suppose there is no minus sign. If I say ux is equal to plus this and uy is equal to plus this, okay, so then here minus will come, right?
Yeah. Then it would be diverge,
Why?
wait,
But at the same logic, when r tends to infinity,
it's the same then.
yeah,
It
na,
will it
same
will
na.
still be 0.
Yeah, you're right. So whether they are converging or diverging, it matters on the fact that what are the equation? There are some other equations also. Depending on the u to uh, psi, na. Psi. Yeah, actually, the solution we have done is by plotting. Okay, from the limit. But if I think from another perspective, minus, even if it is plus, okay, anyway. For irrotational flow, yeah. So it is already irrotational. E is equal to minus grad phi that we already do. Del, there is some other equation also. Del u del plus I d psi 0. Converging or diverging, there are some limiting conditions. Okay, so basically the thing is, yeah, it will be converging, but the logic is, you heard of this conserving the area, right? So yeah, this is the plot. Yeah. So if you do the plotting, so yeah, you can see it is converging. But the logic is, you can see the area, right? At infinity, the area will be more, right? So this is a irrotational. The area will be more, but at like very near to it, the area will be less. So for the streamlines to conserve, it has to be converging. Okay, to because the area times the number of streamlines should be conserved. But if that is infinity, like at zero, it is also infinity. So not infinity like very high number. So to conserve that, it has to be converging. Okay, converging because here, yeah, sorry, this is plus. It is converging, right? So it has to be converging. That logic, but If you just do the plotting, so you'll see that okay, they are like this. Yeah. So that's that. So I think these are the question. Next, I was planning to do the assignment solutions, but I think it is already time. So you guys are okay, or I mean, we can discuss the assignment solution next week then.
Yes, sir.
Okay. If you have any concern or a question, you can tell me because yeah, again, I like if I start the assignment discussion, it will again take some time. But I know the time period is 2 hours, and for me today we already got some little late, so I don't want to keep you for a like long time. So any question till now, or if you have any question, you can let me know next week also. And also the timing is okay, na, from 6 p.m. to 8 p.m. Actually, that's the slot I was given.
This is fine.
Okay, okay. The last time I used to hold sessions on Tuesday and then Friday. Because I also have some workload, so I had to do it Saturday or Sunday. But Sunday I don't want to ruin anyone's holiday. So okay. So thank you all for joining. And if you have any question, you can let me know next week. So okay. So you guys okay. So you guys all are in PSC or like some of you are in MSc?
I'm in my third year of BSMS
You're in third year of BSMS. Acha, where? Acha, BSMS you're
in
saying.
ISER Kolkata.
Acha, Kalyani. Okay, okay. And
Mhm.
others? Others are also BSc or MSc students.
I'm in the second year of my BSc, but
Okay,
my
this
major
time lots
is
of.
computer science.
Acha, we're in BSc Computer Science. Acha, this
Yeah.
time lots of people have joined from BSc. Last time mainly MSc and MSc passed out students were here. Okay. Acha, you guys are in BSc. And others, I guess majority are in BSc.
I'm also from BSc second year, so
Okay, okay. And yeah, you said no. You said I think initially you said already. Yeah, you are in BSc. And others like Manish Kumar and Muskan Parveen. Okay, don't worry. If you don't want to let know, so you can anyway.
By the way, are you a PhD scholar or
Yes, yes. I'm a PhD scholar. So I'm doing my PhD, and
okay?
as part of
So,
yeah,
mm,
yeah.
what's your like topic of research currently?
So mainly, I mean briefly astrophysics, but mainly I am working on the supermassive black holes and their jet emission properties, and yes, mainly theoretical and simulation studies, and but I also do observations
Okay, okay.
in like radio, X-ray, mainly multi-wavelength data.
Um, are you from ISER Pune itself?
No, no, no. I am okay. I haven't mentioned. No. So I am in IIT
Ah,
Kanpur.
yeah. Okay, okay.
You guys are okay. Yeah, do this course fully. I mean, nowadays you can also add this course to your credits, na, in CPI. So yeah, it will be good. Don't forget to put for the enroll for the exam registration and all. Okay. So yeah, you can ask me any question or any doubts in the next sessions also. So hope to see you next time too. Okay. Bye bye. Good night. Sabba khair.
Good
Okay,
night.
good night.
So I'm ending the session. I think. Okay, first I need to stop the recording. Stop recording.